All right. Welcome back to Algebra. We're in Chapter 3, Section 2, Linear Functions. Come on now. This is a linear function. This is not a linear function. All right, we'll look at why. A linear function in a linear equation in two variables, x and y, can be written y equals mx plus b. The graph is a non-vertical line, and it has a constant rate of change. 1, 2, 3. Can be written y equals mx plus b. Constant rate of change. The graph is a non-vertical line. All right, so knowing what we know, let's look at these examples. Is this a linear or non-linear function? Well, this is not a line, so it is non-linear. This is a line, so it is a linear. There we go. All right, if we look at this table, we want to see, is it linear or non-linear? Well, we could graph it and check, is the graph a line? Or we can check its rate of change. So here the difference is plus 3, and here this is plus 3, and this is plus 3. So the difference between each of these is constant, so we have to check here the difference. And the difference here is minus 6. From here to here, minus 6, and minus 6. So this is a constant rate of change. It's negative 1/2. So we have a linear function. Linear right there. Okay, this one we have a difference of 2, and 2, and 2. Down here from 2 to 9 is a difference of 7, and then a difference of 11. We can already tell. We don't need to go any further here, but that is 15. This is not a linear function. All right. Which one of the following equations represents linear functions? We'll say yes. If it can be written y equals mx plus b. No, cannot be written y equals mx plus b. Oh dear. Mx plus b. There we go. That's our explanation. All right. This one is a yes, because we can write y equals 0x, there's no x in front of that, plus 3.8. So that's in the form y equals mx plus b. This one is a no. Cannot be written y equals mx plus b. Nope. Cannot be written y equals mx plus b. This one is a no. Cannot be written y equals mx plus b. This one is a yes, because we can change that distributive property. We get y equals 6x minus 6. And then this one here, anytime you have an exponent with the x, that is not linear, so that is no, cannot be written as y equals mx plus b. All right. There are different representations of functions, and we've looked at these, and so here's a quick review. You can write an equation. If an output is 3 more than the input, more than means we're adding it to, so the input plus 3 gives me the output. Okay, that's the equation. Or I could make an input-output table, right? That looks like this. Plug in a few values, see what I get out. Sometimes they'll give you these values, sometimes you just pick your favorite numbers. We could do a mapping diagram. Notice this is a function because every value in the domain is mapped with only one value in the range. Or we could graph this. And something we don't have listed here, you could also do ordered pairs. All right, graphing a linear function. A solution of a linear function in two variables is an ordered pair, x and y, that makes the equation true. That means you can plug x in, one value in for x, and then you'll get that particular value out for y. Now you can have discrete domains. Discrete means that it's an exact number. There's not a continuous line between them. This is, for example, like the problem we had with the members at a golf club or a country club. Okay, it doesn't make sense to have 1.5 members or 1.7 members, right? So people we would count as integers. However, you could have a continuous domain which goes from one number to the other. Let's say you're measuring liquid. It would make sense to have 1.5 gallons or liters or something like that. So you could have a continuous domain if it's something like that, where it makes sense to have a fraction of a number. All right, graphing discrete data. Here we have a linear function y equals 15.95x. Represents the cost y in dollars for x tickets for a museum. Okay, each customer can buy a maximum of 4 tickets. So, y is the cost, x is the number of tickets. It does not make sense to have a ticket and a half. Okay, so this is discrete data. Okay, can't buy a half a ticket. So your input has to be integers. So if our input is 0, we would do 15.95 times 0. Our output is 0, right? So if you don't buy a ticket, it's not going to cost you anything. But if you buy 1 ticket, it's going to cost you $15.95. So now I have 1 and $15.95. If you buy 2 tickets, you do 2 times $15.95, you get 31.9. And my ordered pair is 2 and 31.9. I can continue this, and now I have ordered pairs. You can take those ordered pairs and graph them. 0, 0 is where you didn't buy a ticket. If you buy 1 ticket, number of tickets are on the x-axis. If you buy 1 ticket, you're at 1 and 15.95. Now notice it's hard to get 0.95 exact, but you're going to be slightly over halfway in between 10 and 20. So fairly close to 16, right, which is slightly over halfway. All right, so estimate 31.9. We're not quite halfway between 30 and 40, just a little over 30. And then here are the other values. So this is discrete data for this function. If we want to graph continuous data, a cereal bar contains 130 calories. The number C of calories consumed is a function of the number b of bars eaten. Does this represent a linear function? Yes, because as you eat, as your numbers of bars eaten increases, your calories consumed increase, and every bar is 130. So it doesn't go up exponentially. Right? If you have the second bar, that's 260. Third bar, you add exactly the same thing to it. B, find the domain of the function. We are eating a certain amount of bars, so the domain here, domain is B is greater than or equal to 0. Right? You can't eat negative bars, but you could consume 0 bars or anything beyond that. And then graph the function. Oh, is it discrete or continuous? It is continuous because you can eat a half a bar or you can eat a fourth of a bar. Then you get a fourth of the calories. So that makes sense. And then we could make a function table again. 1 bar, output 130. Get us another coordinate, 2 bars, 260, 3 bars, 390, 4 bars, 520. And then we can graph that. And this time we've got points, but we're going to connect those points. So we got specific coordinates, but it makes sense to draw a line through them because I could say half a bar and then say, well, that gets me about 70 calories. All right, writing real-life problems. Write a real-life problem to fit the data shown in each graph. Is the domain discrete or continuous? All right, first off, this is discrete. This one's continuous. Okay. Now here we want to find some representation where it doesn't make sense to have a half of something, right? We're going 1, 2, 3, 4, 5, 6. So this could be time in minutes, and this is people doing something, people at a party. All right, 6 people at a party. Every minute, 1 person leaves. Okay, so on the minute, 1 person is left, and after 6 minutes, nobody at the party anymore. For example, or you could say we have coins. All right, if you have coin, and every day you give a coin away. Okay, you can't chop that coin in half, or you probably wouldn't. Half a coin doesn't make much sense, so you give 1 coin away every day. After 6 days, you have no more coins. Whereas here, we would measure something that we can give away a half, or a fourth, or an eighth. Okay, so for example, there's 6 gallons in a tank, and we empty it over 6 seconds. And this is how much is left in it. So, there you go. All right, and that is all for today. Check back in next time for another fun lesson.